Okay, so what we're going to do is look through exercise 31, the further titration calculations. It'll allow you to review your own learning. So question 1 looked like this. 13.2 grams of hydrated zinc sulfate was heated until it reached a constant mass. So you'd be putting that in a crucible and heating it on a Bunsen flame and weighing it and then heating it and weighing it until you got the same mass. That makes sure that all the water of crystallization is evaporated. So all the waters here that are combined within the crystal structure in the crystal lattice are now evaporated and you're left with purely zinc sulfate. We've been asked to calculate how many moles, what this value of X is, of water crystallization there are, given that at the end there's 7.4 grams of solid remaining. So how would we go about this? First thing I would do is look at the equation and put down the information I've been given. So we've been told that we've got 13.2 grams for the hydrated, and at the end 7.4 grams of the anhydrous zinc sulfate, sometimes called the anhydrous zinc sulfate, sometimes called the residue, but 7.4 grams. So what do we do next? Well, the next thing I would do is work out how much water there must have been by the conservation of mass. So if we subtract 7.4 from 13.2, we should be able to find out the amount of water. We get 5.8 grams. So if you manage to calculate 5.8 grams, you would score a mark for this calculation. Next thing I'd do is, in chemistry we never deal in masses because we can't compare them, so we need to convert them to moles, and to convert to moles we need the MR. Now there is no MR for this because we don't know what X is, and X is part of the formula, so we would need it to add up the MR. We do know the MR of zinc sulfate, we can use our periodic table, get 161.5, and we do know the MR of water. We don't need to know the X to know the MR of water now. This is a number of moles in front of it, this is part of the formula. So over here, whereas over here it's a number in front, so the MR is 18. Calculate the moles by doing mass over moles, mass over MR, sorry. Okay, so we get the moles, 0.0458 and 0.322. Try not to over-round at this stage, try to keep 3 significant figures or more. And what we want to do now is work out how many times bigger the moles of water are than the moles of zinc sulfate, and that will give us the value of X. So we're just simply going to take this number, 0.322, and divide it by 0.0458, and that gives us 7 waters of crystallization. This we will round to the nearest whole number because it's a number of waters of crystallization. So that's question 1. Let's have a look at question 2. What we've got is succinic acid, and we've got this formula with an unknown number of CH2s in there, this N. What we do know from the question is that it reacts with sodium hydroxide in a 1:2 ratio. So what information have we got? We've got 2 grams of succinic acid that were dissolved in water, so we're making a standard solution placed in a flask made up to 250. That will be in our volumetric flask. We then poured some of that into the burette, and on average 18.4 centimetres cubed. This will have been our average titer value. We're required to neutralise this. Now this must be in our conical flask. 25 centimetres cubed is the amount we pipette, so this is in our conical flask, is sodium hydroxide. So we're being asked to deduce the formula, the molecular formula mass, that's like the MR, and then find the value of N. So where would you start? The first thing I would do is I would try to visualise it. So I've drawn myself a little diagram here. I put the 2 grams into water, 250 centimetres cubed. I've got that in my volumetric flask. It then said we put that in the burette, so I've drawn an arrow, I've put that in the burette, that we used 18.4 centimetres cubed to neutralise 25 centimetres cubed of sodium hydroxide. So we're going to look at all the data and figure out which thing can I calculate moles of, and the only thing I've got enough information about to calculate moles is the sodium hydroxide. So that is where I start, number of moles of sodium hydroxide. See, I've done volume times concentration. I've converted my volume into decimeters cubed because concentration is in moles per decimeter. You can't combine decimeters and centimeters together. They need to both be in decimeters cubed. And so I've got a number of moles of sodium hydroxide. And then I'm going to move around my equipment like this, backwards through my experiment. If I'm going from the sodium hydroxide to the succinic acid, I'm changing chemicals. I need to know how those two things react. I need to know the ratio. So the next thing I'm going to do is look back at that equation and notice that the ratio is 1 succinic acid to 2 sodium hydroxides. Now I've got this one, the sodium hydroxide, and I want this one, the succinic acid, so I'm going to need to half it. And that's going to tell me how many moles came out of the burette in the 18.4 centimetres cubed in order to neutralise it. So I put some indicator in here. Maybe it was some methyl orange, and I was titrating away. And at what point did it change colour? Well, it changed colour when 18.4 came out, centimetres cubed came out. But how many moles was that? And we've used the ratio to figure that out. But the thing is, that's not where we put the succinic acid, we put it into this thing. So what we need to do now is scale up from the burette to the volumetric flask. And we're not scaling up from 25 to 250, we're scaling up, we're following the arrow from 18.4 to 250. So we can see our scale up factor there, 18.4, 250. You don't need to convert these to decimeter cube because they're both in the same unit, so it's just a ratio. And we can see we get this number here, 0.01698. So there's 0.01698 moles in this volumetric flask in here, and that's got 2 grams in it. So if I know the mass and the moles, the next thing I can do is calculate the MR. MR is mass over moles. Find the MR. I've given it to 1 decimal place because the periodic table gives MRs to 1 decimal place. So I've got 117.8, and that was the first part of the question. And the second part said to find this value of N. So if the formula is in total 117.8, we can do a little bit of algebra. 12 add 2 is 14, we've got that N times, 14 times N, and then 2 lots of this bracket, which if you add up the 12 and 16 and 1 is 45, 2 lots of 45 equals 117.8. I can do a little bit of taking away, so I've taken away this bit from 90 from here to get 14, N is 27.8, which basically gives us N is 2. Now N can't be 1.9, it's a whole number, so N is 2. Okay, let's have a look at question 3, and it's another titration. So we've got the information here, and again there's just a little twiddle at the end. We've got to calculate the concentration in grams per decimeter cubed as opposed to the usual moles per decimeter cubed, and it wants our answer to the appropriate number of significant figures. So if we look at the question now, at this point in an exam, what I would be saying to myself is find out the appropriate number of significant figures now, and maybe write it right down at the end of the question by the dotted line. I'm going to look at this. I've got 3 significant figures there. This could be 2, but it could also be 3. This is 3, this is 3. This is a very definite 3 because the first significant figure is here, not the 1, and then we've got an extra 2 zeros. Now they've gone to the effort of putting those 2 zeros after this decimal place. They want us to know about them. So this is 3, 3, 3, and 3, and this could be 2 or 3. So 3 significant figures is the appropriate number of significant figures for the answer. So I'm going to visualise this again as a diagram. So here you go, I've visualised it as a diagram. Here's how much sodium hydroxide I used. Here's how much of the vinegar it took to neutralise it. The first thing I did was I put vinegar into here and diluted it, and then put that into the burette, then titrated it. So I'm going to start with moles of sodium hydroxide again. And then I'm going from here to here, so I'm going to use the balanced equation. Now, it didn't give me a balanced equation, but it did tell me the ratio was 1 to 1 in the question, so I know that the moles coming out of the burette is exactly the same. And then I'm going to scale up from 13.9 to 250. So now I know how many moles of vinegar are in this volumetric flask. What I need to know is how many moles of vinegar are in this pipette at the start. And this is often a step where people go wrong, because they try to scale down from 250 to 25. Now you don't need to scale down here because all the moles in here came from this 25 of vinegar. The only difference between this bit and this bit was that you added water. From here to here you did need a scaling factor because this already had the water. If there was 100 particles in here, there'd be more than 100 particles in here. But the 100 particles that were in here all came from here, the rest of it was just water, so we don't need to scale now. So these two have the same moles. Okay, so this has got the number of moles in here. Now we can work out the regular concentration in moles per decimeter cubed by doing moles over volume, and that's over the 25. And to convert to grams per decimeter cubed, what we're doing is saying that here we've got 1.8 moles in a volume of 1 decimetre cubed. So if you imagine a cube that is 1 decimetre by 1 decimetre by 1 decimetre, a 1 decimetre cube, there's 1.8 moles in it. And the question is just asking you how many grams are in it. So how do you convert moles to grams? Well, you times by MR. So there's a little mark there for adding up the MR of the vinegar, the ethanoic acid, and then a mark for calculating the answer. Okay, so question 4, we've got some arsenic acid, and we're just doing a straight titration. We put 25 centimetres cubed of arsenic acid into a conical flask, and we required 37.5 of sodium hydroxide to neutralise it. We've just got to find it in grams per decimetre cubed. So it's a simpler drawing because there's no volumetric flask. Here's where I'm going to calculate moles to start off with, because I've got a volume and a concentration of sodium hydroxide. Then I'm going to use that balanced equation they gave me to find the ratio. If I've got 3 of these, I'll have 1 of those. So if I've got 3.75 times 10 to the minus 3 of these, I'm going to need to divide by 3. There we go, 1.25 times 10 to the minus 3, that's how many moles are in here. So if I want to find that concentration in moles per decimetre cubed, I'd use this volume. There we go, I've got it in moles per decimetre cubed. And then if I want to convert it into grams per decimetre cubed, I'm going to times by the MR. So there you go, I've timesed by the MR to get the answer. And then question 5. So silicon tetrachloride, when it's added to water, it undergoes the following reaction. 1.2 grams of impure silicon tetrachloride. So what you have to be aware of is that that is not just silicon tetrachloride, that 1.2 grams. There's something else in there. It could be sand, it could be bits of fluff, it could be anything. There's just other things in that 1.2 grams. So maybe there's only a gram of silicon tetrachloride. That's what we're going to need to find out. It was dissolved in water. So when it was dissolved in the water, it reacted to form this hydrochloric acid. And it was made up to 250. Then 25 of that was titrated, and we required 18.7 centimetres cubed of the alkali to neutralise this acid that was made when we added the water. Let's visualise it. We put 1.2 grams in here and we made it up with water. It made HCl. Only the silicon tetrachloride actually reacted, the rest of the stuff just stayed in the flask. We put that into here, 25 centimetres cubed of it, and we titrated it. So we've got a volume and a concentration here, so we're going to calculate the moles there. Then we're going to use the ratio from sodium hydroxide to hydrochloric acid to find out how many moles of hydrochloric acid there are. And we know that the ratio for that reaction is 1 to 1, so the moles of hydrochloric acid in this flask is identical to the moles of sodium hydroxide. Then we're going to scale up to this flask, because we only used 1/10 of the solution, so we're going to times by 10, or 250 over 25. So we're going to find the moles of hydrochloric acid in this flask. Now that hydrochloric acid came as a result of the reaction of silicon tetrachloride and water. So that's this hydrochloric acid. So how many moles of silicon tetrachloride did I have? So I'm going to take my moles of hydrochloric acid and divide by 4. And I'll get the moles of silicon tetrachloride. Now the question wanted me to find out the percentage purity, so how much of this 1.2 grams is actually silicon tetrachloride. So I've got the moles, I'm going to times by the MR to find the mass. So I'm going to take the MR and times it by the moles to find the mass, and then I'm going to express that as a percentage of 1.2, and I get 66.3%.